3.
Good afternoon, and welcome to today's T&D World webinar on driving down O&M costs with underground line sensors, sponsored by PDI Squared. I'm Nikki Chandler, Associate Content Director of T&D World with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit to the questions window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible throughout and during the Q&A session that will follow the main presentation. Please send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the T&D World website within the next 24 hours. You will be notified by email when that archive is available. Now, I'd like to introduce our discussion moderator, Mike Beeler. He's the National Spokesperson for the Power Delivery Intelligence Initiative. Welcome, Mike. Why don't you go ahead and introduce us to today's panel?
Well, thank you very much, Nikki. I appreciate that. And on behalf of the Power Delivery Intelligence Initiative, we're excited to be here with a member, Sentient Energy. And of course, we're going to talk about line sensing, overhead and underground line sensing. So if you look at the slide, you see the membership of PDI Squared, the Power Delivery Intelligence Initiative. And basically, our mission is to help planners and engineers better understand and to be a resource for planners and engineers to understand the total cost of ownership of overhead versus underground. And we work to educate our stakeholders with this membership of contractors, consultants, equipment vendors, and suppliers within the industry. Today, we've got an outstanding session with Sentient Energy, and two of our speakers are going to talk about what Sentient is doing to drive the cost out of overhead and underground in particular, distribution lines in particular. We're looking at what can planners and engineers do to plan the utility of the future, and how can we drive the cost out of operations and maintenance. And with us today is Bhadesh Kaur and Stephen Watt. So I'm going to ask each of these gentlemen to briefly say hello so you recognize their voice. Then we're going to spend about 35 or 40 minutes going through their very nice technical presentation. We'll take their questions as we go. I'll interject a couple of questions here and there, but if you have questions, feel free to put them in soon, and I'll make sure we get them to Bhadesh and Stephen. And then we'll have the last 15 or 20 minutes for Q&A as we go to the top of the hour. So Bhadesh Kaur, welcome on behalf of PDI Squared, and give us a greeting if you would, please.
Thank you very much, Mike. Good morning, good afternoon to our audience here, and thanks T&D World for hosting this webinar. I'm Bhadesh Kaur. I'm part of product management for our underground line sensing portfolio at Sentient Energy. I heavily work with groups from distribution automation to standards to operations at utilities across the country and globe. Additionally, I also represent Sentient Energy as a partner member at PDI Square. And like Mike said, our mission is to help utilities make data-driven decisions toward undergrounding. Thanks, Mike.
Yeah, thank you, Bhadesh. It's great to have you today. And one of your co-workers is Stephen Watt. Stephen, give our audience a greeting, if you would, please.
Hello, everyone. I'm Stephen Watt from Sentient Energy, and I'd like to thank both T&D World and PDI Squared for this opportunity today to share our perspectives on improving underground power distribution.
Great. Thanks a lot, Stephen. Glad to have you and Bhadesh. So Bhadesh, you're going to lead us off. I'm going to let you advance the slides here and talk about your technology and some of the really cool things you guys are doing at Sentient Energy. So Bhadesh Kaur, go ahead and take it away.
Thanks again, Mike. So let's start with the why. Why monitor underground circuits? Well, if you look at the stats here, an underground outage, even though less frequent than its overhead counterpart, is much longer in duration. On an average, It is more than 1.6 times the duration of an overhead outage. On the other hand, if you look at the switchgear makeup, about 80 to 90% of your system is likely made up of field-proven, cost-effective, but manual switches. So with no remote sensing capabilities, your operations team do not have any visibility into those switches and cable sections. But the question is, why is monitoring underground a priority now? What has changed? Well, what has been changing in the last few decades is the age of your cables. Moreover, what has changed is the need to underground more to counter the impact of severe storms and wildfire. If you look at the curve here, commonly called the bathtub curve, there is immense value in monitoring not just aged cable, but also the new ones you're adding. Whether you need to retrofit or augment new underground circuits, line sensing provides fastest time to value for your investment. So the question then becomes, is there a one-size-fits-all solution? Well, while there can be one, we at Sentient Energy believe it takes two types of line sensors to completely address your underground circuit. So we look at it from two different perspectives. From feeder perspective, we may need to monitor up to 12 phases and line harvest power because there is no continuous power supply available. Whereas when you look at from a URD perspective, you're looking at a single phase monitor that can potentially be directly powered from your secondary side of the transformer. While there is an overlap of use cases, there are unique ones too that these sensors must support. And especially with the increasing EV penetration and change in power flow direction at the edge of the grid, gathering data at substation or 1 or 2 points beyond that is no more adequate. Let us now look at how these solutions. Hey, Mike. Yes.
Badesh, let me ask a couple of questions here real quick. Now, you make a great point that the distribution system is changing as we're reimagining the grid, as Southern Cal Edison likes to talk about, and we're going to deploy more mobile storage, more stationary storage, more rooftop solar, more distributed energy resources, and therefore we need to have a much more advanced grid today. I know you guys are doing a lot of work with underground sensors. Touch just a little bit on what you're doing with overhead line sensors as well, and then I'm going to ask you, when your overhead or underground sensors get the data, how does the utility actually get that data from Sentient to the utility in a place where they can actually use it and obtain some value from it? So touch a little bit on what you're doing with overhead, and then how does the utility use the data?
Absolutely.
Or get the data?
So from overhead perspective, we have two different sensors. One that's called MM3. Typically, MM3 goes on your feeder three-phase circuits. And then we have ZM1, which is a zero-amp monitor, which can go into low-load feeders or laterals. So again, even on overhead, we don't think there is a one-size-fits-all because you can have lines which are very heavily loaded where MM3 works very well, and then you have very low-load laterals, remote locations. So there are two different sensors that does help utility in terms of monitoring and saving their O&M as they are kind of, dealing with faults and issues. So that's your overhead side. Now, if you look at the whole ecosystem of sensors, overhead, underground, feeder, lateral, everything combined, there's data that needs to be collected and looked at, right? So to your point, all these sensors are factory programmed to and ready to talk to your control center. So as soon as you deploy them, they're ready to communicate back. And from communications perspective, we support cellular as well as mesh network. And the data that's coming back from these sensors go through a software platform called Ample Grid Analytics System. And that system allows you to integrate all of that sensor data into your choice of system from OT or IT side. To name a few, it could be a SCADA, ADMS, DMS, OMS. all these systems, you can then expose the data collected by these sensors.
Bhadesh, is that software proprietary to Sentient Energy, or is that something that you give to the utility to work with as part of the package, or what?
That is Sentient Energy's, device management and analytics software, and it can be customized, tailored to the needs of the utility as necessary for, each deployment, each utility is different. So we do have the capability to tailor things around.
Okay, good. Thank you.
Okay, no problem. So we have, what we have observed is, having looked at the benefits so far, we have observed at least like 20% or more reduction in restoration time with the addition of remote sensing to underground distribution lines. If you were to split up the restoration process into these four buckets, and imagine gaining like at least 10 minutes in each area, that can cumulatively mean well over 20% improvement in a 2-hour outage. Let us look at what it means in terms of an impact on your O&M expense.
Let me, can I interject a question here real quick, Bhadesh?
Yes, absolutely.
I had a question from a utility. They said, hey, so how much current does it actually take for this line sensing device? So they call it a line harvest current, I think is, let me make sure I got that name right.
Yes.
So there's a little bit of line harvest power to source your technology.
Yes, absolutely. For that, I'm going to jump back to the previous slide to answer it better. So what you're seeing here on the feeder UM3+, it's a line harvesting solution. And we have a solution that can go up to around 8 amps. If you have only about 8 amps or so, you can monitor a 3-phase solution. If you want to monitor 6, 9, 12 phases, obviously we are collecting, 3x, 4x the data. But we can go down to 8 amps line on the UM3+. For UM1, there is no amperage necessary at all because the power supply of this device is getting the power directly from the secondary 120/245, the hot legs of the transformer. So as a result, no matter what the amperage is, the device is always powered 24/7 and doesn't depend on harvesting. One more question that, Mike, I have heard comes up is, all right, you can support 8 amps, but what happens when it falls below 8 amps? So, what happens is if you follow the traditional duck curve where the load falls, let's say under 8 amps in the evenings, late nights. So the device has capacitors, high-duty capacitors in it, which can ride through your low load periods. And, as soon as the load picks up in the morning, it recharges the capacitor, and these capacitors have millions of charge-discharge cycles, so they have a 20-year lifetime.
So you mentioned something about fault location. You mentioned fault location. Does Sentient Sensor actually improve fault location compared with other incumbent processes that somebody might use?
Yes, absolutely. And I'm going to switch back to the slide we were looking at. And so, well, without sensors, you are relying just on the substation data and the breaker data and, static models, and where you're guesstimating locations to be patrolled, and your sign models can show up like, 5 different areas to patrol. What we are seeing is with the GPS lat long from the sensors, with the waveforms and the high accuracy fault magnitude, you are able to input that data into your fault location calculation to have a more precise fault location calculation done and direct your crews the first time to the right areas to patrol. So instead of having to go to 3 different areas and patrol and then come back to the right faulted section, you can have a more very focused patrolling and fault finding time.
Good, thank you.
No problem. So let's try to see how we can quantify this from an O&M perspective. So what you're seeing here is essentially an aggregated data set across, various utilities, outage related information. And typically I'd say, you're looking at about 200 minutes of an outage for an underground event and 1,500 events over a period of time. And but then, so we kind of focused on this row that's highlighted in yellow, right? All the others are different types of, outages, different categories. Now, if I, let's look at how to quantify. So if we start at 1,500 events times 200 minutes per event, we are looking at about 300,000 minutes of outage. Now, realistically speaking, there is no silver bullet for everything. We can impact, let's say, only 40% of that from an O&M perspective. This means even with that low penetration, you're looking at saving about 120,000 minutes of outage that can benefit from remote sensing. Now, if you recall, we say 20% improvement is reasonable. This means a savings of 20% on 120K minutes is about 24,000 minutes worth of reduction in patrolling and fault finding time. Imagine 3 to 4 personnel out in the field and 2 truck rolls at $750 per hour combined, fully loaded cost, you're looking at about $300,000 of O&M. Now, this doesn't even account for, overtime or events happening 2 in the morning. Well, the question at this point becomes is what is worthwhile annual capital investment for such a level of reduction in O&M? And how do I operationalize the sensor deployment to reap such benefits? For that, I will hand it over to my colleague, Stephen Watt, who will walk you through the implementation strategies and to look at a variety of circuits to see how this quantified data can be actually realized. Over to you, Stephen.
Okay, thanks, Videsh. So let's talk about line sensor deployments and how they save time for crews as they search for underground faults. Okay. Now, the top graphic represents a simple radial feeder with 11 switch cabinets and no remote visibility. In the graphic below, we've created visibility at the midpoint, at 6, with a 3-phase line sensor. Now, with this sensor, we've essentially automated an early step in the crew's fault finding process, checking the midpoint or checking cabinet 6. By automating this step, we save the crew about 15 minutes, and they can jump ahead to the next step in their process. If we want to save the crew another step, we add line sensing at cabinets 3 and 9. So now the crew saves 2 steps in their process, or 30 minutes, because they know which quarter of the feeder the fault is on before they arrive. So fundamentally, that's how line sensors save utility time during fault location, by automating steps and eliminating chunks of time from their fault-finding processes.
Hey, Stephen, how long does it usually take for a crew to put one of those line sensors in? If you're going to put 3 in this particular circuit, how long would that take?
Okay, so for the UM3 Plus, we specify 30 minutes for an installation time in a switch cabinet. So even if you add in some travel time, you can install sensing at 3 locations in less than a half a day. And this is an important feature of line sensing, a very quick deployment time.
Good, thank you.
Okay, now we know that most feeders aren't this simple and many have branches. So let's look at how to deploy line sensors on branched feeders. Sorry. There we go. Okay, so what we've got here is a branch feeder, and the first order of business with line is to put some visibility into cabinet 0, right? And this is where the circuit branches. And you're going to need a 12-phase line sensor at cabinet 0 to monitor all the phases coming in and out of that cabinet. And then once you've got that, now your crew is going to know which branch of the feeder has the fault. And the next step would be, like we did on the feeder, is to add visibility at the midpoints. And here we see visibility with 3-phase line sensors in cabinet 4 on each feeder branch. So on a branch circuit with 4 sensor locations, and one of those is 12-phase, 3 of them are 3-phase, we can save the crew 30 minutes when finding faults. So
and
if
Steve, just to clarify, and Steve, this is another utility question. So this is a fault finding technology, not a fault predicting technology necessarily.
Well, it's actually both. We're talking about the use case of fault finding, but as Bhadesh will discuss later in the presentation, line sensors can also be used for fault predicting.
Great. Yeah, a utility asked that question, and hold on, we're going to answer that.
Yep. If the goal is to reduce O&M, monitoring feeders is a good start, but monitoring laterals is equally important. So let's take a look at an example on a URD. Okay. All right. So this time the cabinets in the graphics, the green boxes, are single-phase transformer cabinets. They're not our 3-phase switch cabinets like we had on the feeder, okay? So there's 8 transformers on the top section, 9 on the bottom section. Now, let's say we have a fault on the top section, okay? If AMI outage alarms are available, they're going to indicate that the top section is out, but we won't know specifically where the fault is. It could be on any of the 8 cable segments in the top section. Okay, on this slide, we've added line sensing, and we immediately know that the fault is between cabinets 2 and 5. So there are only 3 possible cable segments where the fault could be instead of 8. So again, with a few sensing locations, you can save several stops for the crew. And let's say a URD stop takes 10 minutes instead of 15, which we used on the feeder. So let's say it takes 10 minutes. That means you're going to cut your maximum fault finding time from 80 minutes down to 50 minutes, shaving off 30 minutes. So you can see you can save just as much time on laterals as on feeders, okay, especially laterals with lots of transformer cabinets.
Are you monitoring those transformer loads, Steve?
Okay, so that's a good question. I'm gonna let Bhadesh handle it, but yeah, on this model, this is the UM1. It's in a transformer cabinet. So in addition to doing line sensing on the primary side, we're also monitoring load on the transformer. So go ahead, Bhadesh.
No, thanks, Stephen. Absolutely correct. We monitor both the primary and secondary side on the transformer. Some of the use cases we have operationalized as of today are, number one, tracking for detrimental loading of transformers to then make replacement planning a data-driven approach instead of reacting to failures. And with, very long lead times for transformers these days, this has been found to be a fairly useful tool for several utilities. Number 2, I would say is, monitoring for voltage dips and other fluctuations caused by presence of solar PV and, DER penetration. And, utilities would want to, they wouldn't generally know about it until somebody picks up the phone and, complains about flicker, right? But the beauty of this solution is if somebody is complaining about flicker, you have the data at your fingertips to actually immediately go take a look at it and see what could be the potential root cause before even you send crews out in the field. And the third piece I'd like to highlight is the use of loading information to confidently close the normally open point during an outage. So, for example, in this circuit map URD loop, if you have an outage out there and you want to close the normally open point to feed from the other direction, knowing that how much the load was before the fault happened, you would know that closing it in will not trip the fuse on the other side or take more people out of power. And at times, this can also lead to a safety issue. But yeah, I think, hopefully that answered Mike. And while I'm at this, let me also take it to another angle of, the value of line sensing and look at the numbers from a slightly different perspective. Oops, I'm sorry. So we have been talking about O&M, but let's look at the numbers one more time, but this time purely from a CMI perspective. If the metric you are using to build your business case is CMI and you can shave off, say, 20 minutes, imagine 400 customers on a feeder is easy number, probably, half of your feeder has more than 400 customers. You're looking at saving almost 8,000 minutes for a given outage. And, the CMI dollar value varies from one utility to another. But, it can easily amount to somewhere in the ballpark of $10,000 to $12,000 per outage. This can be used as a baseline for trials, and then a more detailed model can be built out as necessary, which inputs, other parameters that is unique to the utility. For example, like, how quickly you can deploy and what are the trouble feeders, what % of your feeders you want to look at. So I would say, this is another good way to look at it. But in addition to one of the questions Mike mentioned from utility participating here was the preempting faults, right? So in addition to responding more effectively to faults, line sensors can also help you identify, potential faults before they happen using something we call disturbances. Now let's look at what that means. What that means is, if you're looking at your underground system out there for, 40, 50 years, there are hundreds and thousands of sub-cycle events that happen every day in your cable system. But most of them don't get caught by typical relays and other IEDs that are looking for, a 3-cycle, 3,000 amp fault, right? Surges. What we can do is with our UM3 plus UM1 solution is monitor for quarter cycle blips that increases over time. So if there is an increasing trend of such blips happening over a period of time, it could be a leading indicator for an impending failure. And while there is always a level of uncertainty with anything that is probabilistic in nature, at the same time, it also provides you the opportunity to proactively perform maintenance instead of dealing with an unplanned outage. And many, like I was saying before, many times these unplanned outages can happen like, late at night, early in morning hours, and over time can be a, very detrimental effect on O&M. So with that, I'd say, look at it from both O&M, CMI, and reducing your unplanned outage perspective. And I'd like to summarize some of the key points that we have looked so far. And
well, hey, Bhadesh, I'm going to add just real quick. I think that's one of the things that the membership of the Power Delivery Intelligence Initiative is really promoting, is that we need to look at the total cost of ownership of an asset. So now here's a technology that's going to help us to allow us to quantify some of these cost of outages. I love your CMI analysis there, putting actual dollar values on the cost of an outage. And then what we want planners and engineers to do now and in the future is to take that into their evaluation. I'm going to look at a T&D asset. Am I going to go overhead? Am I going to go underground? How am I going to build this asset out? And I need to look at the total cost of ownership over the life of the asset. And I think this sensing energy technology You're probably going to confirm that, but I think the sentient energy technology is one of the technologies that we have in our toolbox here for the future.
Yes, totally agree. And just to summarize, put it all together, think of line sensing from three different angles. First, it helps you greatly reduce outage duration when one happens. Second, it can get you continuous monitoring of developing events and the fact that it's a good leading indicator for impending failures. And the third, line sensing can be a major driver to positively impact your O&M spend. And with that, I'd love to take any other questions, Mike, that you want.
But yes, I think I probably robbed you of your concluding remark there. I apologize for that. I think that I got a little excited about your CMI analysis there. So we've got some time for questions, and we've got some great utility questions that have come in, so thank you. And we're going to go right into our utility questions here. Not everybody's from a utility, but many of these are. And feel free to continue to send in your questions. Okay, Stephen and Badesh, first question is, how far apart are the underground sensors placed, and how far apart are the overhead sensors typically placed?
Stephen, you want to take that?
Well, the low-hanging fruit, I'd say, is putting sensors at the midpoint, right? That's the first thing that people do. If they have a complex circuit or they have a lot of reliability issues on the circuit, they can go further and go to the quarter points of the circuit. But really, each feeder is going to be kind of a unique example, and there's lots of different ways to deploy sensors on there. So there isn't really a single answer to that.
Yeah, and I think you did give us a number of different kinds of examples. So here's another question from a utility. What kind of weather conditions can these sensors withstand? Temperature ratings, waterproofing, ultraviolet, things like that. What's your take on that? I guess this would be the overhead sensors.
I can take that. And I was going to actually answer that from two different perspectives, Mike, one from overhead, one from underground. I think, when you look at overhead, imagine the Cat 4 storm in Florida a few weeks back, right? So we have thousands of overhead sensors out there. So the overhead sensors are something that you got to build which can survive that kind of storm. And I'm super excited to say it did. And it's continuously exposed to UV. It is exposed to dust, wind, rain, whatnot. And whereas on the underground side, the challenges are slightly different. In underground, you're not so much getting rain, but the sensors or components of it can be submerged for long duration of time, especially when you're talking about the transformer, right? Switch cabinets, it's a bigger form factor, so it's not probably mostly submerged, but the other factors are, humidity and the fact that the sensors are wrapped around the cables, and the cables, if you have a cable which is like 300, 400 amps of current going through it, that's hot, and that has continuous vibration, right? So it's temperature, humidity, it's UV for exposed components, it's shock and vibe. It is whether IP67, IP68 in terms of submersibility. So we have a full suite of about 25, 30 different tests we take our sensors to, and typically what we do is we work with our customers to share those test reports. A lot of it we have in-house facility which is inspected by third parties, and we have a big lab in Frisco where we can run a lot of these tests, and then we also engage with third party vendors to actually take our products out and get qualified and certified. I think that
Hey,
hopefully that
we talked
answers.
about how much time it takes to install these sensors. A utility question is, does it take an outage to install the sensor?
Yes and no. So both. Let me answer the feeder example first. So UM3 Plus, if it's being installed in a dead front cabinet, you do not need to take an outage. You do a gloved install. There is no exposed energized part as such. If you are installing in live front, yes, definitely I would say you take a cabinet level outage. But for the UM3, if you're dead front, you can do hot install. For UM1, which goes in a single phase pad mounted transformer, our customers have done installs in 15 minutes. And those are all gloved installs too, no outage necessary. And for the overhead, it's a hot stick install, so no outage necessary there either.
Okay, good. I think that answered another question as well. Tell me a little bit about the data ownership. So you're going to get data off of these line sensors for both overhead and underground. Who owns that data? Is that utility data, and are they on their own for doing something with that, or do you have algorithms that you're willing to share with them? And then really the second part, and the most interesting part of the question is, does Sentient Energy take that data, maybe anonymous data, and then take that as an industry-wide data set to develop algorithms for industry-wide benefit? Can you comment on that, Badesh?
Yes, absolutely. Mike, I'm going to answer the second part first, which is, does Sentient Energy use the data across utilities to kind of, build models? Well, I think the short answer is no, because there is sensitivity around the data we are collecting from the field, right? And every utility, so there are T's and C's we sign up with every utilities, and there's cybersecurity aspect to it. So we cannot just gather the data from 5 different utilities into a single system. While that is the state of affairs today, I think I know where you're headed. I think the future is towards more sharing to build something more powerful without compromising security. So we are definitely actively looking at ways to circumvent the cybersecurity concern and deliver something that's valuable. But we are not there yet. To answer your first question, which is who owns the data, so I think just the raw data, the voltage current measurement data, the utility is buying the sensors, right? And Sentient has ownership of any refined data that is coming out of the device. So, for example, let's say we are taking 1,000 measurements and we are running some algorithms on the edge in the device to then output a red, green, orange indicator saying good, bad, or needs attention kind of output. So that is proprietary in nature, but I would say the raw data, the utility.
Okay, thank you. I got a kind of a tangential question here. Let's just ask it real quick and then move on to something else. It has to do with harmonics. Do these line sensors impact harmonics? Do you have to derate a transformer potentially due to harmonics? Are you guys familiar with that at all?
So I would say there's yes, especially in case of single phase pad mounted transformers. What happens is you would see harmonic content because of inverters and things like that, and especially when you have solar and EVs charging in the back end of it. And if you have home to grid power flow happening, so I think yes, we are able to capture those, but we are not at a point where we can actually say exactly here is what needs to be done. So I think like I said, UM1 came out Earlier this year, we had very exciting results. We actually tracked actual fault in the field and transformer overloading. But yes, I would say harmonics is definitely feasible with the existing hardware. Think of the hardware as a platform that has already been developed, and these are all applications like on your iPhone that can be built over time, and doesn't need to be kind of a single shot thing.
Okay. Here's another, this is a really good question here from another utility. Okay, now I have a mix of overhead and underground along my circuit. What type of placement would be best if the circuits have a mixture of overhead and underground throughout the length of it?
Yes, absolutely. I think, typically I would say, let's say you are coming out of, again, I'm going to use one example and there can be 5 other variations. So I'll use an example where you are coming out of substation into a overhead feeder. So you'd put MM3s on your feeder head, and the feeder goes along. Let's say there is a dip pole riser, and then it goes underground, right? So you put a second set of MM3s on the riser there, and then it goes into a single phase URD. You would put UM1s in there, right? And then let's say from that feeder you have a branch to laterals. You put ZM1s in those, right? So I think the best way, what we typically help utilities is when we start a engagement with a utility, we say, let us look at a couple of circuits where you'd like to trial pilot, and we can look at that circuit and provide a placement model, a recommended model that will give you the fastest time to value, and then kind of build on top of it. And what we have seen work best is the model that Stephen was sharing earlier is, let's first bisect a feeder, then trisect, and go from there on.
Good. I got a question here from a co-op. Can you share any real-world examples of cable degradation detection or cases where a cable failure was prevented and remedied before a fault occurred? Kind of, again, this predictive maintenance concept, if you will. Great question. Thank you.
I would have loved to showcase an example. Wasn't part of the deck that we are covering here, but yes, we did have real world cable failure that has happened, and we were able to kind of help with the distance to fault calculation. And I'm happy to kind of please do contact us. We have several case studies that we can walk you through in depth on how we can help on that for sure.
Okay, here's a question from Canada, and going to test you right off the top, guys, Stephen and Badesh, on the IEEE standards. Are your sensors tested to IEEE 495? And 495 is, okay, the IEEE guide for testing faulted circuit.
That is correct. IEEE 495, we are compliant with that, and we are keeping an eye open for the upcoming standards revision. So yep, all the sensors are qualified for it.
Very good. Okay, another utility question. Are sensor placements for overhead best near the cross arm, or is there a certain distance? For underground, I assume sensors need to be placed beyond where the concentric neutral is pulled back so it can see the primary current flow. So where are these sensors located on the actual structure or on the underground circuit?
Okay, let me answer the underground first, and then I'll go to the overhead. So for underground, I believe the question is the sensors needs to be placed beyond where the concentric neutral. Yes, that is correct, and you are absolutely right, because if you are so think of an XLPE cable. You have a neutral pullback, a blade which is kind of pulled back, and you want to place the sensors about 2 inches below where the pullback starts. And the reason for that is 2 inches gives you enough electrical field, magnetic field that we can accurately measure. And a lot of sensors out in the market requires you to precisely center and be 90 degrees to the cable and things like that. But our sensors has been tested for, even if it is kind of tilted at an angle, doesn't matter. It doesn't compromise the plus minus 1% accuracy. We comply with something that's from IEEE 495 called adjacent conductor immunity, which means if, let's say you have two medium voltage, the three cables, phase A, B, and C are 7.5 inches apart as per the IEEE standard, then, the measurements on phase A is not impacted by anything on phase B or phase C. So we do go through all those tests too, and happy to share the details. Feel free to contact us on that. I think there was a second part to it, which is overhead on the cross arm. Well, the overhead, yes, you're right. You're probably going to be closer to the cross arm, but I'm not aware of any specific reason for you to be closer to the cross arm, for that matter. There is a reason to have, again, things may vary depending on the orientation of the feeder cables, whether it's horizontal or vertical. Yeah, the placement may vary a little bit. Our install guides provide you, directions on what are those different options and how to place it appropriately. So we do have, pictures, videos, things like that to augment your install.
Good. So I got a couple more questions here from the audience. And so audience, if you've got any final questions, go ahead and get them in. Second to last question here right now is, how does the sensor act during an unbalanced load case? And also, does it detect high resistive earth faults? What do you think about that? Is that?
Yes. Yes, so I can definitely talk about the unbalanced load or phase imbalance. So we have, and the earth fault situation. So we have two different capabilities I wanted to highlight here. One is, so these triplets, as we call it, these three-phase sensors are on a feeder, and we have a dashboard which kind of shows you phase imbalance across your circuits. And you can drill down from a region to a substation to a feeder and see which phases have the imbalance and appropriately take action. From a specific fault type, we do have classification that we can do, whether it's a phase-to-phase or phase-to-ground or phase-to-phase-to-ground fault. And, essentially an earth fault happening. And accordingly, so what happens is the three sensors, census data, ample analytics platform actually collates the highly precise timestamp data to then overlap the timestamping and actually report that, saying what type of fault it is. I think I answered.
Let me go back to a couple of utility questions that I missed here. So here's the question: when you say blips in quotes, what is that partial discharge?
Yeah, great question. So I think partial discharge is, I would say, is a broad bucket umbrella for, and partial discharge may exist even in a fully perfect system at levels that is not considered to be detrimental, right? So the blips, when I'm talking about the blips, what I'm talking about is, let's say, 3x of your normal rated amperage for a quarter cycle. And that can be because of partial discharge. It can be because of, termination failure down the line and so on. So it can be for various reasons. It is very difficult to, classify and say this is exactly the reasons. What we have observed is even though we have, a tremendous amount of data available, it can be narrowed down to one of three possibilities, saying that, all right, we are seeing a problem and it could be because of A or B or C, and most likely reason could be A. But I think, it's we're not there where we can say like we are 100% certain that it is A and this is what it is. But yeah, I think, what we are seeing is utilities are interested to just knowing that there is a problem and that, the field work or inspection can be prioritized accordingly rather than, just saying like this is exactly, that's the, future next step, I would say.
Okay, here's that second utility question that I wanted to come back to. What type of costs are we talking about for a single three-phase unit with power harvesting?
I am happy to share pricing related information. Please do reach out to us. Happy to help you with, costs and price related information as it, outside this.
That's a fair answer. Okay, here's another utility question. Do the sensors work with an OMS system, with an outage management system?
Yes, absolutely. So, like I was saying, the data collected from our sensors can be integrated with any system, OT or IT downstream. And we believe, in fact, integrating the data into your OMS is crucial, because then as your dispatchers are, working with your OMS, DMS, ADMS system, they can actually use the data from the sensor to more, make an informed dispatch planning and work order and everything to direct the crews. So I think, that is a very important piece. Pretty much all of our customers take the data to that level. We also have what we call APIs, or application programming interfaces, where the data can be piped into any system of choice, and those, cybersecurity measures can be configured and work with the utility.
Okay, so gentlemen, here's our last utility question. We're almost to the top of the hour. We'll wrap up after this last question. From a utility, since most faults tend to be single line to ground, have you developed a neutral sensor?
So what we look at is there are ways to look at it. We do not have just a neutral earth fault monitoring sensor. We use three-phase sequence decomposition to actually look at whether there is zero sequence current available and what's the magnitude, duration, and all of that. So there is a programmatic way to do that. There isn't a earth fault sensor, but there are ways we can help address that, and happy to dive deeper into and elaborate further on how we can solve that problem.
Okay, so Bhadesh and Stephen, my last question is really about planning for the future system, this new reimagined grid that we have to develop as we move towards a more complex interconnected grid with distributed resources in it. It's not going to be our grandfather's distribution grid anymore. It's going to be much more complex. I'm pretty sure I've heard that you say that your overhead and underground line sensing equipment not only solves for driving cost out of the operations and maintenance, but also helps planners and engineers plan the future system. Can you just comment on that a little bit, on how the data that you guys get off the overhead and underground lines can actually be used to help planners and engineers plan a future system?
Yep, I can take a stab, and Stephen, please add your thoughts too. So you're absolutely right, Mike, and I'm going to tag along one more thing that you had mentioned a few weeks back in a T&D World article is, 50% underground by 2040. I think, That's a very sticky idea. I mean, I can't get it out of my head. And if you look at it,
good. That was
even that.
Hey, Badesh, that was meant to be provocative and make people think and have a little bit of a debate in our industry. So good. Thanks for sharing that.
Yeah, no, I think, indeed it is. And when you look at that, what you mentioned earlier is no different is, we can't achieve that in a grid that's built out like, 70, 80, 100 years back, right? And what does it mean really, right? It was designed for a one-way power flow. It was not designed for everybody kind of, adding EVs or, HEVs, whatever it may be. It was not designed for, solar panels on the roof, right? So with all these changes, what has happened is I first start from system planning perspective, right? So system planning was typically done based on, power flow models and how many, what's the square footage of a typical residential home and how many offices and so on, right? And built out that way. All of a sudden, now you have to account for all these other factors. And the good news on that is with DR penetration, you also could also look at how to right size your transformers, right? And do you need a 50 kVA or do you need to overbuild to a 75 kVA? And how can you optimize your CapEx spend there across various buckets? For that, you have to make a data-driven decision, and you cannot just rely on one data point coming back from your substation. You need to have measurements, oscillography along the way to be able to make those educated judgment calls to build the system of the future. But I'll let Stephen add anything.
Yeah, I'd just like to say for the planning team, I think they're usually most excited about the load data because they can get accurate load data at more locations at 5-minute intervals. So they can, they've got a lot more visibility and they can do their job better. They can plan better. They can prioritize asset replacement more effectively, et cetera.
Yeah, I think that's well said, gentlemen. I think that's a real important part when we talk about line sensing. So we're pretty much to the top of the hour. I'm going to ask you too, Stephen. I'll ask you to start with giving us your concluding remarks and any kind of closing greeting that you'd like to give us.
Okay. Thanks, Mike. So a couple things stand out to me. Underground inherently is more reliable. You'll see fewer faults underground, but you have to think about outage duration because it's consistent that outage durations underground are much longer, and we think that the line sensing technology is very well suited to underground for this reason, because line sensing, has a strength to reduce these outage durations. The second thing is, think about the quick deployment time for line sensing. So imagine giving your control room operators full visibility of a feeder in 3 additional locations in less than a half day. Okay, so that means you could add visibility of your top 10 feeders in under a week. Okay, so that's pretty exciting to me.
That's very interesting, Stephen. Thanks for sharing that. Badesh, take a minute and give us some concluding remarks. I know you wanted to mention some of the really great details and resources that you have on your website. Go ahead and take it away.
Yeah, no, thanks, Mike. I think, I greatly appreciate everyone joining here today and listening throughout. I think, I love the questions that came our way. I think very insightful questions. And very, very, meaningful one. As I said, my apologies. Everything couldn't be answered here. If something we couldn't, there are resources available on PDI Squared website where you'll find a lot of case studies around undergrounding. You can also go to Sentient Energy and our blogs. Under our blog section, you'll find, nice write-up around how to think about a pilot. And if you also go to our website where under the underground EOM3 product line, you will find the underground line sensing value calculator. So if you're interested in inputting some, just like 4 or 5 parameters to look at the line sensing value, you can do there. And with that, I'd say, I look forward to engaging further and help you strengthen your reliability and resiliency plans, both from PDI Square and Sentient perspective. And happy holidays, everyone.
Thanks, Videsh. I appreciate that. I do think that line sensing is part of the grid of the future, and as we build a more advanced, a more robust, and more resilient grid, line sensing is going to play a big part in it. So thank you to Sentient Energy, and on behalf of the membership of the Power Delivery Intelligence Initiative, thank you. Have a great day, wonderful holiday season, and be safe. And Nikki Chandler, back to you.
Thank you so much, Mike. That concludes today's presentation. For today's, those questions we didn't have time to answer, we'll be getting back to you via email. I think we got through a lot. And then on behalf of T&D World, I'd like to thank PDI Squared for sponsoring today's webinar and Sentient Energy for an interesting presentation. And of course, thank you all for joining. Have a great rest of your day.